Okay, welcome back to the Octoberfest. And I'd like to introduce our first speaker, Kristof Kanalas of Masaryk University. Go ahead.
Thank you very much for the possibility of presenting. And I want to talk about categorical logic. And for that, I want to start at the very beginning. So how categories appear in logic. Yes. So if we have some signature and we have an S structure over that, then we can think of that as a subcategory of set. So like if we have a group, then we can think of that as a subcategory of set, such that the objects are the definable sets and the morphisms are the definable functions. So those functions whose graph is the interpretation of a formula in our L structure. And so this is how categories appear in logic. And if we look at this category of definable sets, then we see that this is, so every object is just the interpretation of a formula. Every morphism is just the interpretation of another formula. So there should exist some abstract category of formulas such that all these L structures are functorial images of that. And this is true. And for that, there are two preliminary observations or things that we think. That if you look at definable sets, then for certain diagrams, the limit or the colimit is also definable. Like if you have two definable subsets, then the union is definable with this junction of the two formulas. If you have two definable sets, then the product is definable by a conjunction plus renaming those variables which are common. Like, yeah, if you want to take the product of phi x and phi x, then of course it won't be phi x and phi x, but it will be phi x and phi x prime. But in any case, the product is also definable. And so therefore, the idea is that the formula defining this limit or colimit should already be a limit or the colimit in this abstract category of formulas. And these evaluation maps or these models should preserve them. And so if we believe that we can construct this category of formulas such that the L structures are certain limit or colimit preserving functors to set, then the question is, what are the natural transformations? And it depends on what are the formulas in this category of formulas. So we will have components at the formulas defining the full underlying set. And moreover, we have these naturality squares. So if they commute, then this map between the underlying sets will preserve the formulas in C. So if our category of formulas consists of positive existential formulas, then the natural transformations will be the homomorphisms. If it consists of all the formulas, then the natural transformations will be the elementary maps. Both cases are interesting, and luckily the second one is a special case of the first one by some process called moralization, so there's no need to develop two parallel categorical logic. We can focus on the first case. So a positive existential formula is just an atomic formula. I mean, a formula built up from atomics, conjunctions, disjunctions, and existential quantifier. And the coherent formula is just expressing the containment between two such definable sets. And the coherent theory is just a set of coherent formulas. Now on the categorical side, a coherent category is just a category with finite limits, pullback stable image factorization, and pullback stable finite unions. So these are those limits and colimits which are definable in this fragment. And so unions are coming from disjunctions, image factorizations are coming from existential quantifiers. And a coherent functor is just one which preserves all these limits and colimits. And the fundamental fact in categorical logic is that these two things are equal. So there is a process which takes a coherent theory and transforms it into a coherent category. That will be this construction of creating this formula category. And there is an inverse to that. So out of a category, we can form a theory. And yeah, so this is one part, or this is one direction, that out of a theory, we can create this category of positive existential formulas. And that will be a coherent category, such that really the models of the theory are the same as coherent functors from this category of formulas to set. So by taking evaluation of the model. And if we want to concentrate to this process or this syntactic category created out of the coherent theory, then this is how we construct it. So the objects are positive existential formulas up to renaming the free variables, and the arrows are those formulas which are whose interpretation in every model is the graph of a function. So T proves that this is a graph. Yes. So it's written like that. And yeah, so the graph is a subset of the product, and for every element in the domain, there's a unique image of the graph. And if we, yeah, so this is a category, identity is defined by this formula, composition is defined by this other formula. And so if some x is taken to z by the composite, that is the same as there is some y, such that x is taken to y by the first map and y is taken to z by the second map. So this is a category. And one example of this abstract limits and colimits given by formulas is this image factorization, so that if I have an arbitrary map, then this will be its image factorization. And the reason why this is interesting is that if I start with a monomorphism, so now mu is a monomorphism, then the first map in this image factorization will be both effective epi plus mono, so then it will be an isomorphism. And therefore it shows that every subobject in this syntactic category can be represented by this canonical form subobject. So this is a formula which has the same free variable as the codomain, and the embedding is just the diagonal. And so this is the formula for the diagonal. And that's good because it says that subobjects of some given formula in this formula category are just formulas implying it up to T provable equivalence. So that means that this construction, this syntactic category, sees all the Lindenbaum-Tarski algebras. So one can think of this as just gluing together all these positive existential Lindenbaum-Tarski algebras. Yes, and this is the other direction in this equality, so that one can also create a theory out of a category, and these two processes are inverses to each other. So then that's very good because we can translate all the logical questions to purely category theoretic questions, and conversely. And therefore, somehow we can use the toolkit of model theory and the toolkit of category theory at the same time. So that is very promising. Yes, so now let's start working with this setup, with this bijection between logic and categories with some exactness notion. So start with some coherent category, then essentially it's part of the definition that every object, the subobjects of any object form a distributive lattice, and the pullback map is a lattice homomorphism. So we have this functor from CTOf2 distributive lattices, and we can post-compose with this equivalence taking prime filters on these distributive lattices. And so if I have a prime filter on the subobject lattice of X, then its pre-image will be a prime filter on the subobject lattice of Y. So this is a functor, and this composite is called the type space functor of C, because it sees the type spaces in a given sequence of variables. And so this is the definition or the construction that I want to study. The goal is to define some distributive lattice invariant of models. So take this subobject functor and look at its left cone extension along the Yoneda. And now we can, so this will give us a functor from, now I restricted it to just Lex functors from C to Z. Out of that, to distributive lattices, and you can restrict it to coherent functors. So then you will have a functor from models of your theory to the category of distributive lattices. And now the goal is to understand this functor. Yes. So a first step, like how to start, is that since we only care about the Lex Copry sheaves on C, the recipe for computing this left cone extension, which says that take a functor from C to Z, write it as a colimit of representables, then apply this sub C functor on that diagram between representables and compute the colimit in distributive lattices. That is the recipe for computing a cone extension. So we can do that because in this Lex word, or all these category of elements are filtered, so we will have to compute filtered colimits, and we can do that. So this is the diagram. This is a filtered colimit, and one can write up explicitly what it will be. So the objects are just monomorphisms with a marker corresponding to an element of the codomain. And so one object from one of these subobject lattices. And when we spell out what this equivalence relation of being identified in some later stage means, then it means that two such monomorphisms are equivalent if there is a monomorphism to the product such that this pair AB is in that monomorphism, and it has the same intersection with U and V, then we transfer that to the product. And logically, since there is this bijection between the categorical and the logical word, we can also translate it. So the lattice associated to some model is the set of closed positive existential formulas with parameters from M up to, again, some equivalence, where we say that phi A is equivalent to this psi if there is some positive existential formula such that AB satisfies it in the model and T proves this equivalence. Yeah, so I also drew a picture of what that means. So we have one such monomorphism, yes, this from U to X, and we have an object, we have an element A somewhere in MX. We have another one, V to Y, and another element B. And now what does it mean that this first decorated monomorphism is equivalent to the second decorated monomorphism? It means that there is one formula, one positive existential formula, he, such that in that model, this element, this pair is contained in that formula. And in all other models, or in every model, or equivalently C provably, the intersection of this formula with the stripe over U is the same as the intersection of this formula with the stripe over V. So this is the equivalence relation in this left cone extension lattice. And so this has some immediate consequences, that now if A and B are both in the subobjects, then the two decorated monos are always equivalent. because you can take just the intersection of these two stripes, yes, and that is a positive existential formula. So that is a good witness for the equivalence of those two decorated monos. And when one is there and one is outside, then they cannot be equivalent, yes, because then this red dot is in one of these forbidden squares or rectangles. So you cannot contain it in some formula satisfying this this condition that it has the same intersection with the two stripes. And when both points are outside, then the answer is who knows, because then this is a condition, yes. So you cannot say that take the intersection of the complements, because that is not a positive existential formula. So either there is such a formula or not. And this is a lattice. Now, yeah, I want to say, when is it true that the answer for this question is always yes? So we will see that that is called positive closeness. So these are the positively closed models. If I have two functors, let's say Lex functors on some Lex category, then we say that a natural transformation is elementary if the naturality squares at monomorphisms are pullbacks. And yeah, so if we think of f and g as coherent functors and as models of some theory, then what does it mean that this naturality square is a pullback? Yes, if pullback very far. Here. Yeah, so what does it mean that this is a pullback? It means that the map between the underlying set not just preserves the validity of a tuple at the formula phi, but also reflects it. And in the logical language, these are called immersions in this positive existential setup. Yes, and then there's a statement that for some model of some theory, the following are equivalent. The first one is that for every map out of it to any other model is an immersion. So yeah, every natural transformation out of it is elementary. And the second is that if some formula is false, then there is a witness why it must be false in the model. So like, if I have a formula and an element or a tuple which is not satisfied, which does not satisfy this formula in the model, then there is another formula containing that element, such that already the theory proves that the two are inconsistent. Yes, or in the categorical language, if you have a monomorphism and some C outside the image of that monomorphism, there should be another monomorphism containing that element, such that already in the parametrization category, already in C, the two subobjects are disjoint. And yeah, in this case, the model is said to be positively closed. And this second condition is precisely what we need to have an always yes here, because yeah, so you can apply it for this union of the two stripes. That is some positive existential formula that is a valid subobject in our coherent category. And if A and B are both outside, then this pair AB will be outside of this union. So you can contain it in some he, and that he will satisfy what we want here. And conversely, if so the statement is that M is positively closed if and only if the associated lattice is the two-element Boolean algebra. And this argument was from left to right. So if it is positively closed, then since we know when two such decorated monos are equivalent, because it only depends on whether the decoration is in the subobject or not, everything is either equivalent to top or bot. And conversely, similarly, so if something is not equivalent to top, because the decoration is outside of the subobject, then it must be equivalent to the bot, which is this empty set contained in the one element set. And the witness for this equivalence gives the key that we want. So yeah, so we can think of this associated lattice as something that is measuring how much the model is not positively closed. So some examples is that if our coherent category is a distributive lattice and our model is a prime filter on that, yeah, so coherent functor out of lattice to set will land in the two-element Boolean algebra, yes, because it preserves the terminal object and it preserves monos. So such a prime filter, if we want to compute this associated lattice, then we will get this quotient of the original lattice by the congruence generated by the prime filter P. And another example is when you are axiomatizing non-empty sets and all set functions between them. So you take the empty signature with just one sort and nothing else, and you have this theory that you want to look at non-empty sets. Then there is an explicit description of the associated model, the associated lattice. Yes, and so we have some quantifier elimination, so we can only concentrate on atomic formulas, and those atomic formulas will only be able to explain or express equalities between elements. And yeah, if you quotient out with the equivalence relation that we studied, then you will get this description of this lattice. So in this picture, you have to think of this grouping of the elements as the equalities. Yes, so this grouping is the formula A equals B, and yeah, this is the lattice that you get. So let's go back to the abstract definition of this lattice invariant of models. It was defined by a left-hand extension, and a very important adjunction in category theory. It says that this always has a right adjoint, some home functor. Yeah, so in this case, this home functor. And if you spell out what that means, you will get this. So yeah, for every left exact functor on C and every distributive lattice, you have this isomorphism. And now you can take K to be the two-element Boolean algebra. And then on the left side, you will see lattice homomorphisms to 2. So that is the same as prime filters. So on the left side, you will see the just the prime filters on the lattice. And on the right-hand side, you will see natural transformations from F to, you have to first apply the sub-object functor and then mapping to 2. So that is this composite, yes, spec after sub C, which we denoted by SC and called this the type space functor of the model. Yes, and this is the explicit bijection. So this is an instance proving that category theory is just permutating the letters until they make grammatical sense, and that is what one has to do to get this bijection. But now that we have this bijection, we have a guess of some element of the right-hand side. Yeah, so if you have some coherent functor that is a model, and then there is a natural transformation from that model to the type space functor, which takes an element to its type. Yeah, so those monos, which such that A is contained in the evaluation of that subobject. And so the first thing is to look at what that corresponds to on the other side, and it will correspond to the singleton of the top element. So that gives this corollary that for this lattice invariant, the singleton of the top element is always a prime filter. And the other consequence is that now a model is positively closed, so every homomorphism out of it is an immersion, if and only if type M is the only natural transformation from M to the type space functor. Yes, because M is positively closed if and only if the associated lattice is 2, and that is if and only if there is a unique prime filter on that. Now we can push this a bit further, So to study the crude dimension of this associated lattice. And this is the idea for that. So take a sequence of homomorphisms. Yes, take a sequence of natural transformations. For every model, there is a type natural transformation to the type space functor. So we have all these n+1 many natural transformations from M0 to the type space functor. And the idea is that if my homomorphisms are proper surjections, then none of these triangles can commute, because like commuting means that the map is an elementary map, and in particular it should reflect equality. So it cannot be a proper surjection. And moreover, since these are surjective, also no later track. So like also the composites cannot commute, and this gives us a long chain of prime filters. So that way we get out of the model theoretic condition of the model, we get a lower bound on the crude dimension of the lattice, and we can also get an upper bound because well, that's just easy. This associated lattice was formed by some filtered colimit of the subobject lattices, and if all those have at most n dimension, then also the colimit will have at most n dimension. Yes, and still from this abstract definition, we can study the functorial properties of this lattice invariant. So since our left conic extension is a left adjoint, it preserves all colimits. It preserves all strong monos, because every strong mono can be written as some filtered colimit of such strong monos between representables. And those strong monos between representables are coming from effective epis in the coherent category C. So you have to just check that those by this subobject functor are mapped to injective maps, and that is true pulling back along the effective epi is injective. And if C has disjoint unions, then also this left conic extension preserves finite products, because on the Lex functors, since you have to compute the filtered colimit, this coincides with the left conic extension of the functor from CTOf to set, yes, when you post-compose with the forgetful functor. And we know that if some functor preserves finite coproducts, and also finite products, and also its left conic extension preserves it, because finite products form a sound doctrine. And finally, I just want to say some last direction, that in Lüri has some very nice lecture notes about categorical logic on his website. And there is a very interesting theorem in that, which says that if you have a coherent category, then regular functors on that to set are the same as coherent functors from C, now not to set, but to sheaves on some Boolean algebra. So that is very interesting, because it says that even though, like, at the first sight, regular functors on a coherent category, they do not make too much sense from a model theoretic point of view, as they are some models not preserving unions or something like that, not preserving these junctions. But they do make model theoretic sense, because they are just Boolean valued models. And so then we can hope that maybe also for regular functors, this associated lattice will have some connection. The algebra of this associated lattice will have some connection to the model theory of the Boolean valued model. And so this theorem is an instance of that. If C has disjoint coproducts and you have some regular functor on F, then if you compute its left conic extension lattice, then it has these two properties, that the Boolean algebra of complemented subobjects is isomorphic to the Boolean algebra appearing in this when you want to see your f as a Boolean valued model, which is just f2. So there is some Boolean algebra structure on f of 1 coproduct 1. And the other thing is that this map from the associated lattice to the ideal completion of B, taking some x to all those complemented subobjects which are below that, is a homomorphism. So we have some retraction like that. So if we think back to the coherent case, then F2 is just 2, because F preserves coproducts. And therefore, this retraction is just saying the existence of a prime filter. And if you look at what this prime filter is, it is precisely the singleton of 1. So this is a generalization of that. And these are the references, and thank you.
Thanks very much. Let's thank the speaker.